We've talked a bit about interference and how it works. Now let's talk about what it gets used for. Any device designed to produce interference can be referred to as an interferometer. There are many kinds of interferometer, both contemporary and historical. Perhaps the first of these was Thomas Young's double-slit apparatus. Young was trying to demonstrate the wave nature of light. But no one had been able to get interference to show up by using independent sources of light, since they're generally incoherent with one another. What Young did was to take a screen and make two tiny pinholes in it. He then let light fall on that screen, and the light that came out of the pinholes constituted two strongly correlated sources that were coherent enough for interference to occur on a second screen held some distance away from the first. There'd be a pattern of light and dark fringes on that screen, showing conclusively the wave nature of light. More applied, this contraption immediately provided a method for measuring the wavelength of light, as the distance between consecutive fringes on the screen depends on the separation of the sources and on the wavelength of the light used. Since then, we've come up with considerably more sophisticated interferometers. Most people in modern physics hear about the Michelson-Morley experiment, which established beyond reasonable doubt that there is no background ether through which light propagates. The Michelson interferometer used in that experiment looks like so. There's some kind of beam of coherent light coming in from one side. Nowadays that'll be a laser beam, but in the past it could also be collimated light from a sodium vapor lamp or something like that. Any reasonably monochromatic source would do, since monochromatic light tends to also be coherent light. There's a beam splitter that takes half the light and reflects it one way, while letting the other half pass. Oftentimes this beam splitter is just a piece of glass with a very thin layer of silver on it. Then we have two mirrors on either arm of the interferometer, reflecting the light right back. Much of that returning light makes it through the beam splitter and reaches the detector. If the two arms of the interferometer are identical, the light that reaches the detector from one arm will be in phase with the light that reaches the detector from the other arm. After all, it started out as a single source before we split it. That light will then constructively interfere and give us brightness. But if we do something to make one of the arms different from the other, it may be that the light from one arm gets out of phase with the light from the other arm, leading to destructive interference. The easiest way to do that would be to make one of the arms longer than the other. If you move one of the mirrors back by a quarter of a wavelength, you create an effective path length difference of half a wavelength, since the light has to go down and back. And if you make one of the mirrors freely movable so that you can change the path length at will, you can scan through bright and dark fringes by moving the mirror. Knowing the wavelength of the source then lets you measure small changes in distance by counting how many bright and dark fringes go by. Or, if you know by how much you're moving the mirror, you can measure the wavelength of the source, again by counting fringes. This can be an extremely accurate way to measure distances and/or wavelengths. And measuring distances is so broadly useful that it'd probably be faster to list what these aren't good for than to list what they are good for. For example, Michelson interferometers make extremely poor jockeys. Quick note, sometimes you'll see a Michelson interferometer with a slab of glass right here. This is a compensator plate to make sure that the light going down each arm ends up traveling through the same amount of glass, since generally one of the arms spends more time in the beam splitter glass than the other. A minor variation on the Michelson interferometer is the Mach Zehnder interferometer. We still have an incoming beam of coherent light and a beam splitter, but after that, the two arms of the interferometer are held separate until they get recombined at the end. This has the disadvantage of being a bit trickier to align, but the advantage of having widely separated decoupled arms. I'm not an expert on these things, but supposedly they're really popular for analyzing fluids and plasmas in real time. If you put, for example, a candle flame in one arm of the interferometer, that flame and the hot air surrounding it will have a different index of refraction than the rest of the air. And changing the index of the interferometer medium changes the effective path length of that arm, and so will lead to an interference pattern. From the pattern of fringes, you can back out information about the density, composition, and/or temperature of whatever you shoved in there. And also note that this kind of characterization is generally very non-invasive. You can look at a thing without disturbing it. which can be pretty handy.